Okay, so using supercomputers efficiently. Now, no matter what you're doing, even if you're trying to run something that's super parallel, there's always going to be some part of what you're doing that is sequential. What that means is even if you're running like 1,000 threads, they're all running their own tasks. There is going to be a point at which you need for them to finish to do something else, right? So they all have, there is a sequential portion to it. So these threads will run, then something needs to happen, and then maybe more threads can run. So there's always a sequential element to the program, okay? Things that need to happen in a certain order and can't run at the same time as everything else, okay? So for example, it may be, to give you an example in real life, it may be that I can, have the oven baking something in the oven and using the stove at the same time. Okay, maybe I'm frying something and I'm also baking something. I can run those two tasks in parallel, but I also before I ran those tasks, I had to prepare what I was putting in the oven. And I can only, maybe if I was using a chopping board, I can only use the chopping board. Like I'm only one person, I can only chop one thing at a time. So before I even got to the parallel portion, and then after the parallel portion, after I finished cooking, then I have to, I'm only one person, so I can only take one thing off the oven or the stove at one time. So there's always going to be a sequential portion to what you're doing. Okay. And we've got Amdahl's law. And what that basically indicates is that for a given problem, the improvement you get in parallelization will actually plateau eventually as you add more processors. So you can see, let's say that you have a task that is 95% parallel, down to 50% parallel. Adding more processors will give you a speed boost up until a point, but then it actually plateaus. So for example here, we're seeing this growth in the parallel portion, in the 95% parallel task, as we add more and more processors, as we double the amount of processors. But then eventually, once we get to the top here, there's very little difference between 2,048 processors. Okay, that gives us roughly very close to a 20 times speed up, and adding 65,000 processors. So there's actually no additional benefit to using that many more processors, even though that's like an order of magnitude higher, right? We don't get a speed boost out of it. So the solution to running things fast is not to throw more processors at it, because as you can see, it will plateau eventually. Okay. So we need to understand how to then improve the efficiency of our processors so that we can get the speed ups we need. Okay. And what I want you to start thinking about is this idea of latency. So latency is the time that it takes for data to be transferred to a processor. And it depends on where the data is. So if the data is in the CPU cache or in RAM or in a solid state disk or a hard disk drive or another supercomputing node, excuse me, that latency, and this is real world time, transferring the data to a processor, there's a 3 nanosecond latency within the CPU. Taking it out of cache, still on the nanosecond scale. Taking out a RAM, it's slower, but it's still on the nanosecond scale. Taking it from a solid state disk, or in microseconds now, hard disk drive, again, nanoseconds. And from another supercomputing node is in the millisecond range. Okay, so there is time involved with transferring data to a a processor. Here we have, if it took 1 second, if your internal CPU was 1 second, this is what these tasks would look like in comparison. So if your brain runs at a frequency of like 1 second, 1 thought per second, let's say, then transferring data to your equivalent of a supercomputing node will take 3 to 30 years. Okay? So this is kind of what we're getting at. These numbers are very, very small to you, but on the scale of the PC, 1 second compared to 3 to 30 years, that's kind of what we're looking at. And I've just noticed that Fatma has put in the chat the next flow training that's coming up at Pawsey, which is not part of the internship, but you're all very welcome to attend and register if that sounds appealing to you. Okay. So depending on the work that you are doing, and I'll get to the chat in a second, but depending on the work that you are doing, the limitation may come from IO or memory or processor. Okay, so basically, you might have an IO bound process where the speed of your speed is limited by how quickly you can do input output. So transferring the data between RAM and disk drive. Okay, I need to take data out of disk and put it into RAM. That's an IO bound. Okay, it could be memory bound, which is how much time it takes to get memory from RAM or VRAM to the processor. Or it could be processor bound, which is how fast the processor actually works. Like, what is the clock cycle speed of the processor? So depending on what you're doing, you will come in against one of these walls. Okay, so let's look at some examples here. So we got Alice. So Alice is working on an astrophysics project that explores how light is scattered in stellar atmospheres. She's using Monte Carlo simulation, which simulates the path of thousands of individual photons based on randomized starting conditions and events. As a part of each as a path of each photon is simulated independently from each other, this part of her work is embarrassingly parallel. Okay, remember, embarrassingly parallel means that these tasks don't need to talk to each other. Each photon is being simulated independently, so they actually don't need to check in with one another. They can just go forward by themselves. That's embarrassingly parallel. Okay, so Alice would use MPI on Photonics to simulate 1 photon per her CPU core. But now, because each of the simulations, let's say she has tens of thousands of photons, those simulations might complete very quickly. So she may have tens of thousands of photons, but they may take that an individual simulation may take a couple of minutes. So if Alice were to, if the result of each simulation would be completed and then saved as it was completed each time, now the simulations can run quite fast, but now we have this issue of a memory bound, right? Where saving the result of each simulation to memory would result in her work being memory bound. Okay, so how do we resolve that? We can resolve that by saving the work in chunks of multiple simulation results. So rather than accessing RAM every time, we can actually set it up so that we can decrease the amount of times we actually need to access memory or disk. Okay, so that is one way we avoid that bottleneck. Yes, actually, you are right. I think that was supposed to be microseconds. Yeah, that is. I did think that looked a bit funny when I came across it. Yes, And as you can see about normalized time, that is probably correct. So we're looking at microseconds here. I will amend that on the GitHub. Let me just make a note to do that. Yeah. Okay, now let's look at Bob. So Bob is working on a computer vision project that is a machine learning project. He is tasked with training a neural network on a large data set. Bob is working on Topaz as GPUs excel at performing the mathematical operations used in machine learning through shared memory parallelism. Bob finds that his work is, again, memory bound, as he can fit only a small number of images in the VRAM of one GPU on Topaz. Okay, so how would Bob address this? So Bob solves this by using the Horovod Python package, which allows him to train his neural network over multiple GPUs, with each GPU learning on a partition of his data set. Okay, so what we've got here is a situation in which we have a limitation in the VRAM of a single GPU. But what we can do is we can use multiple GPUs, and we have now a combination of shared memory parallelization and distributed memory parallelization. The reason for that is we have a shared memory parallelization where we have multiple threads working on the VRAM of a single GPU. Okay, so the VRAM of one GPU, the processes that are working on that would be considered shared memory, right? But we also need to have a distributed memory solution here, and that means because we're distributing it over GPU nodes, what we need to do is actually have VRAM that is particular for different processes as well. Okay, so we have shared memory and we have distributed memory. Okay, so that is an example of how you would resolve a problem like this. Again, we're not going to go through specific ways to do this for your own projects, but what we want you to do today is to begin thinking about these concepts of parallelization, of shared memory, distributed memory, of those bottlenecks that you might encounter, of latencies in communication. This is what we want you thinking about. And then when it comes to your own project, when you have a sense of what you're trying to achieve, then we can have a conversation with you about what it is you're trying to do. Because like with parallelism, there are so many solutions that you can access different frameworks, different APIs, different platforms and packages that you can use to achieve what you need. So rather than going through each one of those in detail, we're just going to give you the overview theoretically, so you understand what's going on at the base level. Okay. And now we'll talk about this final little bit here. Remember, because of Amdahl's law, remember how you don't necessarily get a speed up when you add more processes? So, I mean, you would get a speed up as you double, for example, here in the green program. If you double the number of processes from 8 to 16, then you get a speed up from 6 times to 10 times. Okay, so you're actually getting a pretty good speed increase, okay, as you double the number of processes. But that is not true the whole way across. If you go from 256 to 512 processes, which is a lot of processes, you actually don't get any kind of doubling, okay, in the speed up. Okay, so it does plateau. And what that means is when you are requesting resources on your platform, that means that you will need to think about the balance here between the time it takes and the resources you're asking for. Now, on Photonics, for example, there is a cost to using the resources, and that is usually, if I was to if I were to request 128 cores for 11.2 hours, then that would cost me 90. What's expressed here as node hours. That would be, it would be charged to my allocation, right? But because that cost is a function of both the time you used and the amount of resources you requested, you can see that if I ask for double the amount of cores here to 256, that means I don't need as much time, and that means I get a lower charge. Even though I've requested more cores, I'm charged less. And if I just look at that doubling here at 1,024 cores used for 1 hour, I'm only charged 64 as opposed to 90, which is when I requested, fewer cores. But because of Amdahl's law, so I'm getting to this portion of my program. If I were to jump up to 4,096, I wouldn't get an appreciable speed up. Okay, so I'm actually, the time it would take is not going to be very different from 1 hour. It's going to be 45 minutes. Like, that's not a huge speed improvement. It went from like 11 hours to 1 hour, but now I'm only saving 15 minutes by asking for 4 times more processors. Okay, and that means that I'm going to get charged much more. Okay. Now, on this is specific to using a supercomputer where you have to use, you have to take into account your job allocation. Because you are charged for the resources you use, and I mean charged here in the sense of you are given a certain amount of service units. You have a certain allocation. This is, in terms of the fair use of the system, you need to be a little bit, the word I'm looking for is, you need to be a little bit strategic in what you request. Okay. But if you owned Pawsey, if you owned the entire supercomputer, you wouldn't care, right? Because you could just, there would be no cost associated. So if you wanted to like run 4,000 cores, you could totally do that. So this is what it means by saying here, on a Nimbus instance or your own machine, the ideal configuration is the one that gets your work done the fastest. So if you owned Photonics, if nobody else had access to Photonics except you would probably go for this top one here, right? Because it would get the work done as quickly as possible. The only reason we care about this is because you don't own Photonics. You have to share it with others. And because you have to share it with others, there is a fair use policy in place. You have a cost associated with the things that you run. So you want to minimize that cost. So that's why we go for the balance here of time and cores. Okay.